All right, so here's class 11. We are dealing with buckling. This is the third class in deflection in chapter 4 of Shigley. And here's what we're going to really be talking about today. We're talking about compression members. And the pool noodle is a good place to go. So we kind of already have some experience in real life about buckling. When something is long and slender like this and we push down on it, eventually we're going to find some place where it buckles, right? So we know what buckling is. We kind of have that already from our experiences in life, this phenomenon. But we need to look and investigate it a little bit closer and kind of see how we could quantify what the limits are. So this is a failure mode that's really important because it falls into this category of this sudden and unexpected failure. Like something was working fine and then just a little bit more load came around and suddenly it fails, and with catastrophic consequences. And most often civil engineers would be more focused. I don't want to say most often, but civil engineers have to deal with buckling a lot more than we mechanical engineers. But it's still an important thing to know about. And so I want to try to have like a series of examples and videos to get you familiarized with buckling, even though we won't deal with it a lot, just one class worth of stuff in one assignment. But it is it's an important thing to know about, right? And then later on, if you fall into a field where this might be something that you should consider, hopefully you'll remember some of the stuff that we discussed. So we could categorize buckling in these 4 different ways, but really we'll have one main focus, and maybe 2, really kind of 2 different types of buckling. So we have long columns with central buckling. They're saying central buckling because as you'll see down here in number 3, we could have eccentric buckling, right? So we're going to assume that the load is right in the center of the cross section for this main kind of buckling, and we'll explain why. All right, but it's so this is like an idealized type of scenario. This first one. The second one is an intermediate length, right? So there's really long columns, and then there's just sort of pretty long columns, right? And then, as I mentioned, number 3, we'll say, okay, what happens if we had if the load isn't exactly in the center of the thing? It changes what the results are. And then lastly, if you got squatty, little tiny things that look like columns, but they're pretty short compared to the others. So we want to see really between 1, 2, and 4, 3 categories of columns. We got really long ones, we got kind of in the middle ones, and and 4 is little squatty ones. And we don't really do much with the squatty ones, but we should just realize that we could categorize them in 3 different ways. But this is the way that the chapter in section 411 how they treat the thing. We start out with the concept of stability. This is something you probably already inherently can relate to, right? The first, almost everyone when talking about stability has this like little marble. It's in a ditch, right? And if we nudge the marble, we give it a little bit of a little push. It's going to roll up, it's going to roll back, it's going to roll back. And if there's some like friction involved, right, it'll eventually like stable out and go back into its position, right? And so the nature of the problem is a fundamentally stable position, right? Because it'll self-correct, right? So a small action produces a small effect. That's something that's stable, right? Now here's the counterpart, the unstable situation, right? If the ball is now, instead of in a ditch, it's on a hill, right? If we just give it a little tap, or a fly comes and lands on it and it's going to go crazy, right? So a small action produces a large effect. That's the idea of stability. When we take it to buckling, I think another good one is let's think about your knees, right? And if someone were to a larger friend was to decide that they wanted to do play chicken, or whatever. What do they call that? I forgot. I'm losing my mind. I can't remember what that thing's called. But anyway, when people, they get onto your shoulders right there, and now you got to like run around and somebody else, and they're gonna fight. But if that person's really heavy and you tried to stand, I mean, you could get you kind of put your knee lock your knees. But the heavier they get, at some point, boom, it's gonna buckle, right? So you can think about your leg buckling, right? That it's fine, and then but just enough weight, and it goes Well, you can think of like you have like this little rotating spring, kind of in the stiffness in your knee, and you can kind of get that sense, right? And then some my big head here. We can figure out that at some point with a little tiny displacement, right? If there's like if you just were to bend your knee just a little bit, it would be buckle a lot sooner, right? Well, that's because there would be like a moment that's created between the deflection and the force. If you do a free body diagram, you would see that itty bitty amount of deflection right there creates a moment arm, and now that's like trying to bend and trying to keep your straight leg from being straight and kind of bending it, because if just looking at the one side right there, if it's got like, if the force is going this way and there's a little tiny displacement right here. Okay, that's like the concept. But now we got to put some mathy stuff into it and kind of look here. And we have a good friend that we introduced recently, and he's called the Flexural Equation, and it's going to come up and it's going to be relevant again. So here you go. Here is hand notes, and let me go through this short derivation. This derivation is in some ways a rite of passage, right? This is like one thing where we can say, why did we learn differential equations, and why do we bother learning that, and why did you bother bringing up the flexural equation? We did a little brief derivation of the flexural equation, Euler's equation, right? And I got this little thing pointing right at me. I'll take that out of my nose. Okay, so we have this column situation, and he's pinned down here, and he's pinned here, but he's got rollers, right? So that means the thing can't go left or right or into the paper or out of the paper. He can only go up and down, and he's pinned right in there, right? So it's kind of like just held at a point right there. So there's no moment at that top point, and the same thing true here at the bottom, right? So if you just press downwards, this top thing won't go side, back and forth. It can only go up and down. So as you push right there, we're gonna have, and this thing is pinned, so there's nothing holding it up here. It's just holding it like by a point, right? So let's just assume it buckles, and we could do a free body diagram here. And they decided they were going to go V in this book is going to be the displacement, right? So we're doing an FBD of this, and we take the sum of the moments, and it's got to be equal to 0, right? And so we have a moment. There's a moment on here, and that we could figure out what that moment is, right? If we're taking the sum of the moments about A, we'll say that moment that's up here, and they decided to go plus right here. Okay, so they decided as a sign convention, instead of going plus and minus, they're just going to go like this right here and say this P, this load P, is going to be multiplied by the displacement, and I think I decided to call it Y just because I liked Y better, right? So here is our Y coordinate right there. So instead of V, I'm using Y, but that's just the displacement at this hypothetical thing being bent. We don't know any of these values yet, but we know that this arrangement has to be true. Well, what we could do for this moment is we could replace it with our good friend, the Flexural Equation, right? If you recall that this was the second derivative of that deflection with respect to its axial position, plus Py equals 0. Okay, so what we've just done, just from an FBD and the Flexural Equation, is we set up a second order differential equation. Second order differential equation, and we usually like to arrange that so it's like, let's get rid of anything on the front side of that. And I'll put this in parentheses, go P over EI. y equals 0. Now, the reason why you take differential equations is so that I don't have to teach it to you. But we know the solution to the second order, this very fundamental second order differential equation, or I hope we do. But I will teach you the thing that made it most clear to me when I finally the light bulb came on, that I understood what the hell we were doing in differential equations. I mean, I made pretty good grades in undergrad, but I didn't really understand it. It was when someone said, all differential equations is the mission to try to figure out what kind of thing, so what kind of thing does that, right? And so so by saying that, it's like when they said that, I was like, oh, I got it. Okay, what kind of thing, when you have the original thing, but then you take the derivative of it twice, when you put them together, will turn into 0. What kind of thing behaves that way? And the answer is it's a sine function, right? When you take the second derivative of a sine, you get a negative sine. And you add negative sine and sine together, and they equal 0. So if you have something, y equals sine, with some good junk on the inside of the next to the angle thing, and you take a derivative of it, and then you take a derivative of it, and if you add it back to the original thing, it's going to cancel out. It's going to go to 0. Well, a cosine will do that, but actually a cosine and a cosine, they're the same thing. They're just shifted over 90 degrees. Or you could even say, well, e raised to the something, with imaginary number up in the raised to the thing. When you take the second derivative of that, that will be negative e to the thing, right? Add them together. But it turns out e raised to the imaginary number is actually a sine and cosine added together, right? They call it the Euler equivalency, right? So that's actually, they're all the same thing. They're all a sine function. Is the only thing that exists in this world that when you take the second derivative of it and you add it to the original thing, will cancel itself out and turn to 0. So it's the only solution to this that's possible. Now, as a general solution, what they like to do is cover all the bases. And so we stick a magnitude in the front of this, and we take the sine, and then this has to be by the square root of it, right? It's got to be the thing on the inside, because it's going to fall out when you take take the derivative of the thing twice. It's going to be multiplied by itself and become this, so it's got to be the square root of that, right? So it's a p over ei. And I hope what I said had some amount of usefulness to someone out there, all right? So anyway, but it could be a combination of a sine and a cosine, right? It is possible in lots of different scenarios where this could be a thing. So this is like a generalized solution to a second order differential equation, but we could start making it a little bit more specific to our situation. And the way that we do that is with boundary conditions, right? We say we know at x equals 0 that it's not allowed to deflect in the y direction, that y is equal to 0. And then we, if we say that, if we say x equals 0 right here, if that's true, this can't be true, because cosine of this is going to be equal to, of 0, right here, because that's 0, is 1. So that's b. But right here, if we take the sine of 0, that's going to be 0, right? So we have to have a situation, if we put in 0 here, and this becomes 0, we put 0 in here, it becomes 1, this has to equal 0. Therefore, b must be equal to 0. That's the only way it can happen. We don't have any choice. It's just a fact. It can't be. Okay, so all of a sudden, we got rid of the cosine. That was nice. We didn't want it anyway. And then we have the other boundary condition, that at the length of the thing, all the way up here, at x equals to L, y is also have to be equal to 0. Right? So when we do that, for the only way that can be true, right? It is not going to help us out figure out what A is, but it will tell us that the inside of this thing right here, right, when that's L, it'll tell us that this thing has to be some multiple of pi, right? Now, it could be, one of the solutions is possible, is that the square root of p over ei, it could possibly equal to 0. What ei times L? Sorry, ei times L, right? Square root of p over ei times L could be equal to 0 and achieve this, but that's not possible. No. Okay, so that's not a solution. Another solution is pi. Pi is the thing that's when you're inside here, right? So it'd be this right here, when you put it together, could be 180 degrees. That would make sine 0, and then yes, it would obey this thing right here. Another is, it could be 2 pi, right? It could be 360 degrees. It could be 3 pi, but you get the idea. So we decide that we're just going to say that all of these are some integer times pi is the solution to this buckling scenario right here. And so what we solve for, let's solve for p right here. And by the way, we got to square this other side. So we're going to have n squared and pi squared, right? So do I want to bother with the, I guess I could just right here, we say that p, I'm going to solve for p, because that's the thing I'm about to know. When does it buckle? I want to solve for p. And what I end up finding is I got n squared and pi squared, and I have ei, and then I also have L squared right here. And so this says PCR. We're going to call that the critical. This is the critical load. And that critical load is now going to say, okay, so one thing that we do know here is that when n is equal to 1, this is going to be the smallest load possible, the smallest load at which this thing fails. And so we go, that's pi squared ei over L squared. Okay, and we're almost done with this video, and we'll move it on to the next one. But this was just for this pinned boundary condition. So by the way, this is the Euler buckling equation. Or we call it Euler buckling, right? We're going to add something to this just to make it a little bit more useful in other situations. So these boundary conditions that we had right here might not be the only boundary conditions. Like, okay, so we could take a look at these particular types of things. So here's the boundary conditions we just did. But they might be fixed at the top, right? So they might be fixed in such a way that this thing can move up and down, but there's no moment. So one of the conditions is now the slope has to be 0 here. So those are boundary conditions that could exist, right? We could also have one where this thing is allowed to go side to side, but the slope, it has to be 0 back down here. And then another one where it can't go side to side, but so this is pinned fixed right here. So we have fixed free, that's this situation right there, fixed free. We have, they're called rounded. I'm trying to think of what the heck they mean by rounded. I'm trying to see where's rounded. That's just occurring to me. Like, I think that's pinned. Yeah, that's what that is. That means pinned, which is this is the typical situation that we have, pinned. And then we have fixed pinned, that's this guy. And then we have fixed, which is this guy, right? So let's see. Fixed free, you can think of that as just cantilevered, right? That's just this thing, and you put a force and it can go over to the side, right? But the base is held fixed, is cantilevered. All right, so these are like end conditions, and we could have come up with some things for boundary conditions, but we'll just accept that we have the critical buckling load right here is going to be equal to some C that we're about to just talk about, pi squared EI divided by, I'll keep capital letter. And by the way, in Shigley, this is equation 443. And this is Euler's buckling equation. Let's see, do I want to bring up the next things? Yes, I do. I think I will, and then I'll go to an example because it isn't much longer. Okay, but this is for long and slender. Long and slender columns, right? So really, really, really long. We might start to back off, and we can. Okay, so another thing. This is not maybe the most favorite. Okay, well, I should mention what C is. Damn it! I should edit this video, but I'm going to keep going. The C is a factor that accounts for these different ones, and you could see, no pun intended, what they should be, right? So let's talk. These are the theoretical values, and for us, these are the ones we're going to actually use, right? These others, these are like more like, okay, well, just here's like, well, this one is an important one because the fixed free is this will buckle quicker than the other ones, so that we stick in a value for C. And that's going to make it 1/4 of, like, let's say this is our generic go-to pinned. This is the one that the equation came from, right? So you see that C is equal to 1. But we have other situations here, and we'll talk about. Maybe I should talk about them now. We could talk about the. No, I'll talk about it in a second. It makes more sense in a second. So, so the fixed rounded, which is this guy right here, we'll see that we use a 2 right in there. And then for fixed, we use a 4. So fixed is harder to buckle than pinned. 4 times as hard to buckle. That's what we're learning from there. But we could plot like a trend, right? So we could actually plot out Euler if we introduce something called the slenderness ratio. Okay, so going back up to here, we see that we have the length and the moment of inertia. So these are really geometry things. And so we could introduce something called the slenderness ratio, right? So we also want to recall that we had I. Another way that we can think about moment of inertia is something called the radius of gyration. And unfortunately, not every book uses the same variable, but this book and many others use K as the radius of gyration. So as a refresher, the moment of inertia can be expressed by this K squared times the area, right? These are both cross-sectional properties, so we introduce another cross-sectional property, which is the radius of gyration, right? And that's really just a useful way of describing the section properties, right? We could think of the areas. That's how much material is being used, and depends on what the shape of the thing is. That's going to determine. Right? We could say that, like, maybe this has the same amount. Let's say this has the same area as this, but these are going to have different moment of inertia properties, right? They've used the material differently. Hypothetically, these have the same cross-sectional area. They don't, but let's just say that they do. And but one's going to bend easier or more difficult, whichever you want to think of it in whichever terms, than the other. So we could use this K as a means of, we could say that K is equal to the square root of I over A, right? But we just want to remember that's the radius of gyration. So we can replace that inside of our buckling up here, right? Actually, replace it inside this one right in here. And come up with this thing we call P critical now. I guess we did keep the C in there. I guess I will keep the C in there. And then go pi squared. And now E, right? But we're going to introduce this thing L over K, right? So we're replacing in this equation L over K, right? So we have these two together. And I don't think I did the algebra anywhere. Why didn't I do the algebra? Anyway, you could take it on faith, or you could do it right here, that it's going to end up being L over K squared. And we need an A. Oh, we need an A over here to be able to do it. But I decided we're going to divide this by A over here. I should really show. It'd be a lot smoother. This would have gone a lot smoother if I had done that. Oh well, maybe I'll do that in class. But anyway, what we could have right here is we have this parameter called the slenderness ratio. And so the longer a column is, the more likely it is to buckle. And the lower the K is, or the larger the K is, I should say, the more likely it will not buckle. So it's like the inverse right here. So these are two parameters together that are kind of to decide whether something's going to buckle or not. So the larger this ratio is, the more likely something is to buckle. So we can plot this L over K, and they're using lowercase L's, and it looks a little bit like 1, but it's actually L over K right here. And so that's what this is, the slenderness ratio, and the larger this is, the less likely it is, let me see, I'm going to say this the wrong way. Yes, the larger this is, the more likely it is to buckle, which means the lower the critical force has to be. But we can divide that by the area right here. And then we can kind of think of it as, so they're calling it a unit load, but we kind of think of it as stress, right? We could say that here's some stress that we're putting onto the thing, and at some point it's got too much stress and it buckles, right? So this part of this curve that we're showing is this. But something we want also consider is that at some point, this is, if we keep going up here, we're eventually going to get to the material limit, right? So then, we can't go any higher. Well, what someone has done, and his name is Johnson, has to create this little curve right here that joins the two things. And so we're going to say in this region, and we're going to cover this in a subsequent video, this is the Johnson. This is the Johnson buckling. So we say that Euler, this is the Euler curve right here, and this parabolic curve, which is really a curve fit between Euler right here. At some point we make a transition, and over here this is the long and slender. This is going to be the transition point, right? So we're going to talk about that in a subsequent video. But this is Euler right here. So the Euler buckling is for long and slender, and it's everything over to the right-hand side. And everything to the left-hand side, we kind of assume it's Johnson buckling. We will find that there's sort of a limit where it doesn't really make sense, right? And that's going to be where the squatty columns come into play. Now, the one last thing, and I made the video too long, I didn't mean to. So another way to approach finding this critical buckling limit. Well, that's zooming back in and out right there. Put something in there that can focus on, or is it just going to go wacky? Okay. Instead of doing this C right here, so it's the same thing. It's just an alternative way of approaching this and finding, is to now come up with the idea of an effective length, right? So instead of using equation 443, what we could do is we could have an LE, right? This is the effective length. And we could say that's, if we want to make a transition from that table we were given, that we take 1 over the square root of c and multiply it by the length. And so the P critical is going to be pi squared EA over the effective length divided by K squared. All right, so here's the effective slenderness ratio squared, right? So this is an alternative method right here of doing the same thing, and quite common because of this figure that you see from another book where you have pinned, the effective length is equal to L, right? Here, this one we put this, let's just put that to the side for a second, but look at this one right here. I mean, if you were to cover this stuff up right here, wouldn't that be essentially look like that? I mean, look at the shape of this thing. It looks from right here to right there. It looks like it's pin. So here's the effective length is actually 0.5. And then take a look at the fixed free. Right, here's fixed and free. It's like as if it's the mirror image of from here up, right? Or I say it's only like half the image is this part right here. So it has this kind of mirror image down below right here. So the effective length is 2 times L, right? So looking at these two different situations right here, you can kind of get the idea of why you would want to use the effective length as opposed to using that factor in there. And then this one right here just turns out to be 0.7 times L. And I think this would actually be 0.707. I think it's actually kind of from the derivation of the thing. I think that's actually true because you would actually see we have the square root of the C coming up right here. So if you were to come up in here, for that was the fixed rounded, right? And so that's C for this thing is 2. So down here you would take 1 over the square root of 2, and I'm pretty sure that that's going to be 0.707. Sure enough, it's 0.707. All right, so that was a lot of information, but this is like buckling 101. The most important, this is another Euler, by the way, alt equation, right? So here's the alternate version of the thing by using the effective length. So in summary, when you put a load on something long and slender, it has the possibility of going boing over to the side. And this is the fundamental thing that most students need to know about. All right, so we'll go to the next video. Hopefully this wasn't too long. 30 minutes is too long of a video. Oh well. Well, maybe make it up for it in the example. Try to be quicker in class.